In this video, I'll show you how to use a LQR controller in order to control a boost converter. So this is a basic LQR controller where you use the small signal model in order to get the LQR gain. But with this type of controller, you will get a steady state error. So therefore, we need to add a integral action. In order to eliminate the steady state error, we need to add a integral action. So we can do that by defining a new state variable, which we call x3. So this will be equal to x1, or the integral of x1. So the derivative of x3 would be equal to x1. So we can simply just add that to the small signal model. And this would be the new small signal model. The one state that I'm taking the integral action on is the x1, which is the current. The reason why I wanted to add integral action to the current is because by controlling the current, we can also control the voltage. We could actually do it on both states, both voltage and current, then we get a 4x4 matrix. In order to control the voltage, we actually need to add a PI control for that. The reason why I added a integral action to the current is because the current is the hardest to control and the voltage is pretty easy to control. So we can just add a PI controller for the voltage control. I can show you how to implement the PI controller later, but now we also need to change this circuit because the states that we measure is not equal to the states that we have in this state space model. The rest of the circuit is the same as the old one. Now, in order to control the voltage, we will add a PI controller in order to find the correct current reference. And we can do that by adding this circuit here into the scheme. So this PI controller works by finding a peak value of the current, and then you oscillate it if you want a certain waveform. For example, for a PFC, you will have a sinusoidal waveform, and you may also want to add some offset. But I think in most cases, you don't need an oscillator and you don't need an offset. You just need a limiter because the current can't be lower than 0. And maybe you also want some anti-wind up as well. So you can just add some anti-wind up. In order to make this more robust from a lot of disturbance, you can actually do a trick. So you see that we have a VI in all of the terms in this B matrix. So you can actually take out the VI and multiply it by the change of duty cycle. So you can actually multiply it here. So if this is a multiply box, you can multiply by VI and just remove it here completely and define a new U where U is equal to D tilde multiplied by VI. And what we get out of the LQR is U, and then you need to divide by 1 over, so 1 over VI, multiply by 1 over VI. That was a bit messy, but I think you get the idea. You should do this for example, a PFC, where VI changes a lot. So this is the real-time value of VI, so you can take into consideration the change of VI.